everybody's here to join to this conclusion of 12 years, or 8 years. Not anymore. Yeah, okay, so hybridization is quite common in nature. And with the use of next generation sequencing, we are continuing to understand the consequences of hybrid events and the impacts on species. So I want to begin with explaining what is hybridization. So imagine you have an ancestral population, and then there's a barrier that happens. This barrier can be a physical barrier, it can be morphological barrier, it can be behavioral barrier between this population. So eventually what happens is this population splits. And over time, these two divergent populations begin to accumulate mutations, more and more mutations, and they become diverged. So what happens if this barrier that is separating them disappears and becomes permeable, and they come into a secondary contact? So they've been separated for a lot of time, and now they can come back together. So then what happens is they can begin to reproduce with each other, they can begin to hybridize. So now we have a hybridization event happening here. And the goal of my project is to understand what's the consequence of hybridization at the genomic level and morphological level. So I'm going to explain you some of the consequences using this charismatic model that Gil has been using for years and years. So we have two sortal species that live endemically in Mexico, in quite part of Mexico. So we have Malinche right here, and Birchmanni right here. And as you can see, there's quite a difference morphologically between these two species. Malinche, they have this extension of the caudal fin, it's called a sword. They have smaller bodies compared to Birchmanni. Birchmanni, they have bigger dorsal fins. There's also variation in the pigmentation between the two species. And we can find them in the eastern part of Mexico. This is the Gulf of Mexico. This is my hometown, Mexico City. And right here is where these two species are going to be located, specifically in the eastern Sierra Madre mountains, right on the eastern downhill from these mountains. So as you can see, there's quite a slope. There's an altitudinal gradient where we collect all these species right here. And whoever has been lucky enough to be to the field station is located right in this point between these two mountains. If you haven't, I recommend you to do so. So as you can see, there's a change in elevation. In these parts of the mountains, it's high elevated, and as you go down these streams, the elevation disappears, and eventually you reach the Gulf of Mexico over here. So in these altitudinal ranges, we find Haphophorus malinche, broadly in this area. And they live in these small streams, cold waters, and they prefer to stay in the shallow areas. And on the contrary, Haphophorus birchmanni, they live in the low elevations areas of these mountains, in the foothills. And their environment, their habitat is quite different. So the rivers are way bigger in this area. The temperature is warmer right here. And historically, they have been areas of overlap between these two species. And they have been stable. However, so they have been stable because there's this premating barrier between them. So females from these two species, they can recognize their own species by smell, and they have a strong preferences for their own. However, when human population began to increase, then a lot of localities began to have a lot of participation. And some localities even have Jackson Pollock level of pollution. And in these areas, we can find these two species. So what happened is this level of contamination began to confuse the recognizing of their own species. So this preventing barrier that was in there became permeable to reproduction between these two. So what happened is the two species began to interbreed with each other. And then we have these hybrids. And these hybrids have been, we can find them everywhere in this area where they overlap. And natural selection is acting against these hybrids. So we know that there's hundreds of incompatible genes in their genome. And that level of incompatibility is creating this strong selection against them. So first of all, what is a hybrid incompatibility? So let's go back to that ancestral population I was explaining at the beginning. That ancestral population splits in two, and then each one of these two new populations begin to have a new mutation. So originally there were one gene was big A, and now this population mutated to little a. This one, it was big B. Another new mutation is little b. Over time, that mutation becomes more and more common and becomes fixed. Now, what happens if they hybridize? Then we have a mix of these two mutations that this population right here, they were used to that. And this population right here, they were used to that. But now these hybrids, they have this new combination that was not before. And that incompatible combination can reduce less fertility or higher mortality. And this has been widely reported, for example, in Drosophila hybrids between Melanogaster and Santomea, or also in mice between the German hybrids in Mus musculus and Mus musculus and So, in our fish, I expect that there's going to be selection acting against them. And the interesting thing is that we have this elevational gradient. So I want to know, given that there's this strong selection acting against hybrids, how is that impacting the level of movement, of migration, of gene movement along this gradient? Because we know there's a lot of incompatibilities in them. And also because there's a lot of physical barriers along this gradient. However, even though there's strong selection against hybrids, we also know that sexual selection favors this combination of phenotypes. So when Malinche and Birchmanni are reproducing with each other, this new combination of their genomes generates curious combinations in their phenotypes that females, then they can So this is also quite reported in the past. For example, in the Manacus hybrid zone, females are very attracted to yellow coloration. So then what's happening is in the hybrid zone, the yellow plumage is beginning to introgress. Introgress means it's beginning to move from one population, one species, to another to this hybrid zone. And eventually, they have been reported that yellow coloration is also being common in the other particle species. In swordtails, we know that females, from Birchmanni specifically, they have an aversion to males with a sword. This is by using video feedback and animations. If you show a female male with no swords, and a male with a sword, they will go specifically with the one that has the smaller sword. Females from Malinche, they don't care, so they are like whatever. So we see some sort of selection against this phenotype happening here. So another big question that I have is, how does that phenotypic introgression compares to the genomic introgression that we're going to be seeing in these hybrids? So to answer these questions, as Gil mentioned, I spent a lot of time hiking and climbing and falling and camping. So after years of all that and a little bit of blood, sweat, and tears, I managed to thoroughly collect 12 localities in 2 independent rivers along this elevation and gradients. And as you can see, in some areas, I encounter a lot of physical barriers for migration, for fish migration, and even for human migration. There's a locality just upstream from this pool that, as Paolo can also be witness, it's very difficult to just jump across. As we go down the elevational gradients, these physical barriers begin to dissipate. They're still there, but they begin to dissipate. And eventually, the river becomes bigger and bigger. So I have these 2 independent rivers with 12 localities and multiple collections in small scales. So then after that, I collected a lot of DNA from 807 individuals or so. I did a lot of library prep. We did next generation sequencing. So we did a lot of sequencing and then parsing and priming and banging my head against the wall in order to get the alignments and the ancestries to continue the analysis. So I used multiplex shortcut genotyping, which uses probabilities to tell me if a portion of the genome comes from one species or the other species or both. Basically, what this does is we have 2 references genomes from each of the parental species. So I'm going to take a piece of one hybrid genome, and then this program will compare it to each of these 2 parental genomes, and using probability will tell me, well, there's a high probability that this part of the genome is coming from Malinche. So it's going to give me number 2. And then if it's telling me that it's coming from Birchmanni, it's going to give me a 0. It's like high probability of ancestry. In this case, in these hybrids, if there's high probability of coming from both, I'm calling it heterozygous, so it's going to give me a 1. And I did that through the entire genome with all my individuals. So I could do client analysis. So I can detect introgression using geographic line analysis. So what is geographic line analysis? Well, this begins with John Gordon Sanderson, Haldane, which used the decline analysis to analyze how an environmental gradient affects the distribution and the survival of one population. But then Nick Barton and Godfrey Hewitt took that theory from Haldane and they applied it to hybrids, because hybrids, they also have one gradient from one species to another through this hybridization area, hybridism. And this Klein analysis is powerful and has been widely used, and right now there's multiple softwares in the market that we can use. Specifically, I'm going to be using this one. And now you're like, but tell us what is a geographic line already, right? So here it is. Basically, we have our gradient. So we have a transition from one species to another, in this hypothetical case from blue to red. So we can track the ancestry of multiple genomic regions over the entire genome. So for example, I'm gonna show you gene number 1. So gene number 1, as we move through the transect from one species to another, you can see that the frequency is increasing gradually. Geographic line analysis will tell you multiple parameters. The most important ones are going to be the center. The center of each line is going to tell you the point where you have the most heterozygous individuals for that gene. In this case, at this point in this gradient, in this physical distance, this locality for this gene is going to have the most heterozygous, the most hybrid individuals. The analysis also gives you the width. The width will tell you how quickly it shifts from one parental species to another. And it tells you a lot of information. So if I show you gene 2, what's different? It's narrow now, right? So we can see that the width is reduced. So there's less individuals here. In reality, we should expect them to have 20% from red. But now we see that they have probably 10%. So as you can see, the width tells us a lot of information, and also the center. So in this half of the cline, we can assume that there's selection acting against the red ancestry. And on this side of the cline, there's a lot of selection against the blue ancestry, which is making this reduction in the width. What about gene number 3? Gene number 3 has a totally different shape. And now we see that it's moving towards the red area. And now the center is important now. So the center is showing us that at this point in the physical distance, in this gradient, for this gene, we have a lot of heterozygous. When we expected to have probably around 70%, now we have 30%. So what we're seeing is a lot of selection against red, so the blue ancestry is introgressing in this gene. We can see the same on the opposite side. So for gene number 4, we are seeing that there's a lot of selection against blue, so now having red is favorable, so it's introgressing on the other side of this gradient. And we can compare a lot of them, so we can have a genomic profile. So we have multiple of them, and we get the average. So now using the average, we can overlap each one of our genes to see which ones are having a lot of introgression and which ones are not, or having reduced introgression. So another big question for my project is, how do I know that this one is having reduced introgression because there's selection acting against it, or just because random chance, because of drift? How do I know this is showing that maybe this gene is advantageous, or just having a small population is by chance making this pattern of ancestry? So to answer that question, I did a lot of simulations. So we're going to continue with my hypothetical blue and red. So I simulated 2 big populations and 19 hybrid populations along this hypothetical distance. And then for some of my simulations, I reduced the amount of individuals in each hybrid locality to 100. So very small population. And then I did another set with 500 and another set with 1,000. And then I changed the rate of how many individuals are moving between adjacent hybrid localities. So I set it up to 0.01. This means for these hybrid localities that have 100 individuals, only 1 is migrating each generation. So it's very low. For this one, 10. So that's going to be higher. So I have in my hypothetical individuals, each one they will have 10 chromosomes, and within their chromosomes, their combination is going to be even through all the way. And then, in some simulations, I just let them be and let them reproduce, migrate, etc. But in some of them, in some genes, I apply selection, specifically directional selection. So one gene is going to be advantageous, so it's going to be moving. And in another one, I apply a BDM incompatibility. So there's going to be a lot of selection against hybrids, against this combination of genomes. So I expect a lot of clients with reduced widths. And I let them be and reproduce for 100 generations. And then I took samples of 30 individuals to extract their genomes. And then again at 1,000 generations. And I replicated this hundreds of times per simulation. That's where my banging of the wall. If you go to my office, you will see that. So this is what I have. So I have the genomic profile. I'm showing you just one simulation right here of hybrid localities of only 100 individuals. And 10 individuals can migrate within hybrid locality every generation. So this is the genome. So as you can see, it's showing a smooth change in this hypothetical gradient. So in a gene that I know I'm not applying selection, then I can have a true negative because it's overlapping the genome pretty well. In another gene that I'm applying selection, then we can see this shift on the center. So this is implying that there's a strong integration happening at this gene. So we'll call this a true positive. However, in some genes where I'm not applying any selection at all, we also begin to see some movement. So I'm going to call this a false positive. And moreover, in some genes that I am applying selection that I expect some sort of introgression happening, it overlaps the genome. So I'm going to call this a false negative. So what I did is I calculated the false positive rate, so how many false positives I am encountering in simulations where I'm not applying selection at all. And this is a small example of what's happening. As you can see, a lot of them have very drastic shifts. So in this small population, in this population that have a small amount of individuals, I'm getting a huge amount of false positives. So these are the results of my simulations with no selection. And this is a very complex graph, so I'm going to dissect it. So let's start with populations of 100 individuals and only 10 migrants per generation. As you can see, having a small population has a very drastic effect. It inflates the amount of false positives. As hybrid localities are bigger, the amount of false positives reduce greatly. And very big hybrid localities have no problem. As we reduce migration rates, so instead of 10 migrants per generation, only one, there's less gene flow. So just chance increases, and chance alone begins to shift those clients. So I have bigger false positive rate. So this is in young hybrid zones. This is after 100 generations. After 1,000 generations, this becomes more drastic. This is quite a bad scenario, right? So these are all together again. Now, what's going on with selection? So I have genes with selection and I have genes without it, and I'm seeing the same pattern. But with selection, we can now look at false negative rate. So how many times I'm getting false negatives. So for example, right here, like I mentioned, I'm applying selection to this gene, but is coming as neutral. And this is an example of multiple of 100 replicates of these simulations. So you can see there's several of them that are either coinciding with the genome, and some of them are showing the opposite. Right? So this is the false negative rate that I found. Now it looks big, but just make out that the axis doesn't go to 1. It's only 10% of the time, or specifically around 7% of the time. Small, but it's there, right? So what's happening is in small population sizes, at 100 generations with only 10 migrants, we're beginning to get a lot of false negatives. Possibly because we have small population size, so random chance is there, but we also have these migrants coming in. So just by random chance, the frequency matches the gene. As we increase the age of the hybrid zone, this pattern disappears. So either by random chance, these frequencies become fixed, so they appear as strong selection. So I also did the same with BDMIs. So with BDMIs, this is the pattern I get. So with BDMIs, I got no negatives. Every single one appeared as a strong signature observation. So where are we? Where our system? Where is our system in this case? So we know that hybrid zones, our hybrid zones, are around 50 generations old. Population sizes estimates are about 800 in some localities. And migration, it's been estimated to be good. So not as low, but it's not as big. So we are somewhere in this area. So my expectation, if I have my 2 transects, I have my 2 rivers that I have collected. So my expectation is not going to be a smooth change from lowlands to highlands, because we know that there's a lot of incompatibilities acting against them. So there's a lot of selection against hybrids. Remember this gene, right? So we know that there's a lot of this in our system. So my expectation is that the whole genome is going to be more stepwise with smaller width. So this is what I got. This is the whole genome hybrid index of one of my clients. This is the Huasalingo client. This is one of my rivers. And each one of these triangles is one of these localities that I took samples from. So this is small elevation right here, and this is going up the river to high elevations, to 1,200 meters high. And the first thing that shows is this very drastic change in the whole genome ancestry. From 30% within meters, within 1 or 2 kilometers, it goes all the way to 89%. And what's also shocking is if we compare the second string, I have a replicate, so the other river. First thing, we are seeing the same pattern. It's a quick shift from Birchmanni ancestry to Malinche ancestry. But another shocking thing is that they are not matching the same elevation. They are changing at a different point of the elevations of these mountains. So for example, this locality right here in Huasalingo at 450, all the individuals are around 30%. But at the same time in Puchula, that's where I have most of my habits. So I'm going to show you how this looks like as we go down the climb. So I'm going to show you in the y-axis, this is counts of individuals. In the x-axis is how much hybrid they are. So from Birchmanite to Malinche. And this is what happens. We are in the highest point of my transects. And as you can see, we start with almost pure Malinche. As we go down, look at Huasalingo first, look at the right. Sorry. You can see that it's beginning to change. And then the frequency drastically splits in two. While Pochula, they're still 90%. In Huasalingo, there's a quick shift to 30–40%. Pochula, we still have Malinche. Now, around 25% in Huasalingo. In Pochula, we start seeing some hybrids now. And then, mostly stays the same in Huasalingo. In Pochula, that's where the fun is beginning. And now we're finding the center of the decline at Pochula, while in Huasalingo, it's mostly Birchmanite ancestry right now. So, one of the cool things is we know now where the two centers are from these two transects. And we can do a lot of follow-ups. One of the greatest things is that the center in Pochula, it's like Gil said, it's like for lazy theologians. Because you can drive from the field station to this neighboring town around 40 minutes or so, hop off your van, walk down the downstream the river for a few minutes, and then you will reach this locality that I call Tula. The client center at Huasalingo, though, that's for more adventurous people. We have to drive around 3 hours to get to this very small town away in the mountains. And then you have to hike down to a locality we call Totonicapa for about an hour. And then you have to go upstream to work in city. I mean, it's doable. And actually, I want to go back because this is what is very interesting that's happening here in the Huasalingo. So we are seeing this bimodal distribution of ancestries in this hybrid zone. Totally different from what we're seeing at Pochula. Pochula, all the individuals are within 40 and 60%. They're very hybrid. In Huasalingo, we seem to have two groups, two clusters of hybrids. Some of them are very Birchmanite-like. Some of them, so the pure hybrids are in very low frequencies. And then we have some that are either Malinche migrants, are just falling down, but also some introgressed individuals. And this is very cool because in another independent hybrid zone, this is actually happening in the backyard of our field station. The hybrids have formed completely separated groups, and they mate within their own group. So there's assortative mating happening. It's not at random, and that is also driving a lot of selection against these pure hybrids, and then they have formed these two very discrete clusters. So this other locality, I was telling you, Totonicapa, this is just a few meters downstream from the Huasalingo Center. And what these authors thought is that this event is quite rare. And in here, this group of individuals, there were maybe just Malinche migrants. But what is really happening is maybe they're not Malinche migrants, maybe they are Malinche hybridae from this other assortative discrete group that are flowing down. So this is a nice follow-up to what we can do. Okay, so now I'm showing you the genome, and I told you that we can compare multiple genomic regions against the genome to measure the amount of introgression. I'm going to show you a little bit complex graph right here. We have elevation again, And now each one of these triangles is one of my localities where I collected my individuals. And then on the y-axis, I have the Klein width. So remember, with small width means that the decline changes very drastically. And with a bigger Klein width, the decline changes less drastically. It's a sign of a lot of introgression happening. So here it is. This is each one of my genomic regions that I analyzed in my samples. And what's popping up is that there's an amount of genes that are showing a lot of introgression. But the cool thing is that a lot of them are clustering within the center and are showing reduced introgression. They have very small widths. And also, some of these that have small widths are clustering, are grouping in areas where we have physical barriers. And if we go to Pachula and see what's going on at Pachula, we see a similar pattern. First of all, less of my genes are showing these big widths. The majority in Pachula will have very reduced and step Kleins. And also, this cluster right here appears in an area with a lot of physical barriers. What about all these incompatible genes that I was telling you, these BDMIs, these incompatibilities? So I know the locations of them in the genome, so I can see how they're introgressing in my two rivers. So if I show you here, this is Wasalingo, and each one of these gray lines is one of these BDMIs. As you can see, they have these very stepwise small width shapes as well, with some of them that are able to move around, to introgress. And they're going to be here in gray. So as you can see, only 5% will have these big widths, and the rest will have small widths. And Pachula, this is more drastic. We see less of these genes that have big widths. Most of them will have reduced widths. If we look at the pattern right here, only 0.4% are showing these big widths. 86.2, they have small widths, and even 13.4% are showing extreme reduced widths. All right, so I'm showing you that indeed there's a lot of selection acting against them that is reducing the introgression of all these hybrid genes. But what about the phenotypes? What about the sort, the story that I was telling you about? So we know that Birchmanni, they don't like the sort. If there's a hybrid without a sort, then maybe they will find it very attractive. So given that this is happening, how is the introgression going to be comparing to the whole genome? So we have our Kleins right here. So for this part, from those fish that I collected, I took a lot of measurements, and with help of undergrads, we got all these measurements. So now we can track them along the gradient. So I'm going to show you first the standard length, which is how long the fish are going to be in these two rivers. So this is Wasalingo right here, from low elevation to high elevation, and this is Pachula right here. And I'm putting in a square the centers of the Klein. And as we go down the mountain, we can see that in regions where I find my hybrids, I find the longest hybrids. The same Pachula. We go down, we see that the longest individuals are going to be pretty much the hybrids. So this is something called transgressive expression of morphology. this combination of genomes are allowing them to have bigger sizes compared to each part of the species. And with body depth, we have a similar trend where the hybrids are showing this bigger body size. So what's up with the sword? With the sword, as we go down the gradient, it changes drastically from these three localities in Guasalingo. They are 90% Malinche. And then we drop to our hybrid zone, and the sword pretty much produces in average. The same in Cochula. Cochula is actually more drastic. All of this is around 80% Malinche, and all of these are 90 or more. And then in this one, they are around 60, 70%. The sword on average is also very, very reduced. So we can look in more detail at the two centers of my clients. So we have here the ancestry of Malinche. Again, we can see again our drastic discrete groups of hybrids. Some of them are very Birchman-like, and some of them are Malinche-like. And you can see that there's reduction of the sword. So some of these hybrid individuals have mostly Malinche, but their swords are going to be very, very tiny, more like daggers. And then in Cochula, they all have very, very small swords. If we compare this to body depth, or how big their bodies are, body depth is pretty much even throughout the ancestry. So we can see that if a hybrid has a lot of Malinche in their genome, we'll not predict if they have a big sword or not. So we are seeing some loss of the sword. In here, this is the ancestry of my individuals, and then I'm comparing the average sword extension in Guasalingo, and the same in Cochula. So for example, here, the average is very low compared to their ancestry. So what I did is I took multiple measurements from my fish, and I did a principal component analysis to basically gather all these variation in their shape to get two main axes of morphology. And as you can see, principal component 1 mostly changes with how tall their bodies are, but principal component 2 is going to be changing on how long their sword is going to be. So I can use this principal component 2 and feed a cline along these gradients and compare it to the genomes to assess the level of introgression. And this is what I get. So as we go up the cline, we can see this blue graph is the genome. You can see that the introgression is getting lost. So the center of the sword is away from the genome center. And in Cochula, again, it's more drastic. The center is even more separated from the hybrid genome center. So indeed, there seems to be some patterns of sword loss in these hybrid zones. It's showing reduced introgression. So for all these 8 years of being here in my project, it's an exciting time to study our model system. We know that geographic lines are powerful to detect reduced introgression. Honestly, I want to go out right now, take a bus, and go hike that mountain again to the Guasalingo Center to see what is going on with that structured population. So it will be really interesting if there is indeed reproductive isolation. So selection is maintaining this narrow hybrid distribution, but at what degree is this environment independent, or is just intrinsic selection happening? And we know that assortative mating is also facilitating introgression. In Guasalingo, you saw all these clines with big widths. So maybe it's due because assortative mating is breaking all these incompatibilities and letting them migrate to these other hybrid localities, something that we didn't see in Cochula. And essentially, the method traits are introgressing freely. We see these hybrids with big body sizes, but yet they have these reduced swords. So maybe swordless is a phenotype that is not introgressing as much. Whew. So there is a lot of people to acknowledge here. Mostly Malamates, specifically Dan, that's somewhere over here. Mateo, Marina, who helped me with all the measurements. Molly, who helped me with all the bioinformatics. Of course, my committee members with all the advice. Dr. Heath for letting me use and break his computer once. I didn't. And of course, Clemente Hernandez, who is our field station neighbor. He works with me for a lot of years, and he came with me to all these hikings and helped me collect these fish. I spent about 3 months going up and down the mountains, and Clemente was there helping me to collect these fish. And of course, this wouldn't be possible without my mentor, my advisor, Bill Rosenthal. So I met a lot of lab mates through these 8 years. So these are some pictures of former lab mates and current lab mates and future and new lab mates as well. That's all right, if you don't recognize. And of course, upcoming lab mates. And this wouldn't be possible without my parents that were able to come here. Se necesita de mucha perseverancia y fortaleza para hacer un doctorado. Y ojalá yo tuviera la mitad de perseverancia y fortaleza que ustedes tienen. In English, it takes a lot of dedication and perseverance to get a PhD. And I wish I was as dedicated and perseverant as my parents. So thank you for coming here all the way from Mexico City. And with that, I'll take any questions.